Okay, Tribology tutorial question 1b is a continuation of the previous video 1a. Okay, so this 1b is actually a type of questions with equations. Alright, so a 40mm diameter hard steel ball is loaded under compressive force 100 Newton. Alright, against 60mm diameter curved copper alloy, simulating blah 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 blah. And calculate the Hertzian stresses. This is the Hertzian stresses equation that are normally provided. But the formula for calculating E, the equivalent Young modulus, and R is not given, so you have to be careful of that. And this is the impression radius. Later I'll talk about it. Alright, so given the Young modulus of steel is this thing, determine the minimum level of Brinell's hardness. Alright, so when you talk about Brinell hardness, actually this should be like that smell. Yeah. But anyway, so Brinell hardness is BHN. Okay, so you need to determine the minimum level of this value. Okay, and then you need to avoid, and what is the depths in order to avoid plastic deformations, and we're going to talk about it later. If you remember, the depth is actually 0.6a plus minus 0.1a. Okay, so this a is actually this a. You know what I mean? Yeah. There are a few equations that are hidden that you are not being told, or in other words, you are not being shown over here. So you need to memorize certain equations that is not given to you. Alright. So to understand the question first, alright, I'll just let you understand the question first. So the 40mm diameter steel ball is all the steel balls. Alright, these are the steel balls. So if you take about one steel ball, for example, alright, it's loaded under compressive force 100 Newton against 60mm diameter curved copper plate. Alright, so it's actually loaded onto this copper plate. This is a copper plate. Okay, I also don't know why this is the copper plate. Why not the outer one? But anyway, so simulating contact between the balls and the outer race of the thing. As you can see, this sentence is also a bit weird. So it's simulating between the ball and the outer race. The outer race is this one, ma. So isn't it this ball and this race over here? So therefore, in other words, should be like that, ma. Why am I compressing like that? But never mind, this is the answer. So the answer itself states that compressive force 100 newtons against this copper plate. That's what it's trying to say. So how does this works is that this is the surface, alright, of the copper, this thing. So you have a ball over here, alright. So you are actually pressing it down, alright, when you start to actually move the ball, because when the thing is rotating, most probably is because this thing is rotating. This thing is rotating because the shaft is rotating, right? This thing is rotating. So therefore, there will be a certain compressive force. But because I believe the steel ball is harder than the copper, so this is why the steel ball itself will actually make an indentation. So maybe I should So you actually go into the thing, alright, and you will cause this indentation. So this indentation itself, alright, is something like that. Okay. So this indentation, there will be a certain radius. So we call this the impression radius. Alright, this radius is A. Alright, so our A is our impression radius. So now you get the meaning of what is impression radius. It's an imaginary radius. Alright, due to this impression. Alright, hopefully you are clear. And the first thing you need to do is to know what is R1 and R2. Standard, alright, R1 and R2. R1 is normally the radius of the bearing. The radius of the steel ball. Alright, where this is the diameter 40mm. So therefore the radius is 20mm of the ball. And then R2 is equals to 30mm, alright, of the curved copper. Because this thing over here is 60mm. Alright, and therefore I think you get what I mean already. Okay? So therefore, once you set this thing, alright, next we need to have a certain equations. Alright. Second step is to find your equivalent radius. Your contact radius. Yeah, your contact radius. Alright. Why do you want to find this? Because your equation over here need you to do that. Alright, it's because you are not given any equations or any numbers. So you need to do that. Okay? So be careful that this is called the contact radius. The contact radius. Alright. So the contact radius itself, alright, is taken, although this is plus, okay, but R2 is a minus V, or is a negative because it's a concave. Alright, I also don't know why is it concave. Alright, so R2 minus R1. Oh yeah, I know what I mean already. Okay, so for example, R2 is this one. Alright, so the ball bearing over here, this is R1. Alright, but it is impressing onto the surface of the copper. Alright, so this impression over here will cause the change in the radius. You see? So they will cause this change of radius. So over here, this is in total, this is R2, right? So R2 minus R1, alright, you'll get the equivalent radius or the contact radius R, where this is the point where it contacts. Alright, if you were to bring this ball in, if I were to just give me a while. So this is the point where both of the materials contact, the copper and the ball. Alright, so this is the contact surface, or the contact radius I should say. Alright, so once you get the contact radius out, alright, understood, we can just calculate for our contact radius. So I think it's pretty straightforward already. So R1 we know is 20. Alright, just now we have shown you R1 definitely is the radius of the ball bearing. Alright, R1, or this one, 20 millimeter, while R2 is 30 millimeter. So I'll just sub it in straightforward. Alright, you give me a while. Yeah, so take note that it's a minus because it's concave. Sorry, is it concave or convex? Yeah, concave, because you have this shape. So the radius between the R2, alright, this part over here, this R is actually R2 minus R1. Okay, so I think you get what I mean already. Alright, if it's a convex, for example, alright, like something like that, then it's actually R2 plus R1. Okay, hopefully you are clear. But nonetheless, we are doing concave, so it should be fine. But it's good for you to know. And therefore, coming back here, alright, this is the equations, and then you have this value. So what we have is 0.017 absolute value if it's negative or plus, whatever it is. Alright, so once you switch, please remember you switch, because normally you may have a tendency to careless mistake and leave this as an answer. No, alright, please switch this thing. So 1 divided by 0.017 is equals to your contact radius, which is equals to, it's about 58.28. Alright, so the lecturer write equivalent to 60 millimeter. Okay, so this is the first thing. So please take note that you'll need to memorize this equation, or I forget to say. So where does this equation come from? You can go to page 18, alright, of the Tribology lecture notes. It's over here, the mean contact radius. And then therefore the next thing that I want to introduce you is the equivalent Young modulus E. This is the equation you also need to memorize. It's not given to you anywhere. Alright, given to you in these slides, but it's not given to you in the exams. Okay, so the third step, alright, is to get this equivalent Young modulus. And why? Because of these two equations. Alright, we need to have all this. We have found R, the only thing is E. Alright, so the W, if you think about it, is the load. Alright, W is equals to load, and therefore the load is actually the compressive load, 100 Newton. Alright, and therefore this leaves us with only the equivalent Young modulus to solve. It's pretty straightforward already. So once we solve this, and it should be fine. So we need to know the Poisson ratio. Alright, V1 and V2 and E1 and E2. So how do you actually solve this thing now? Yeah, come to think about it, I still thinking about whether is it material 1 or material 2, or is it direction 1 and direction 2. Okay, because if you think about it, if you were to go into 3D, this is the ball bearing. Alright, then it will actually cause a concave in this part, right? If you were to look into this view, alright, if I have this thing over here, this is the concave part. Alright, so over here there will be how do I say, yeah, if it's 3D view, then this is the one direction, this is the two direction. Alright, and therefore the Young modulus in this two direction is still talking about the steel ball. Yeah, that's also the blur thing also, and this is why I kind of don't know what the hell is going on. Alright, so I think it's still talking about the 1-2 direction. Alright, after thinking quite a while, lady, because if you think about it, the stress maximum stress most probably is caused by the steel ball. or because the steel ball is compressing onto the copper plate. Alright, so the steel ball, since it's talking about the steel ball, then it's talking about the steel ball lah. Okay, anyway, so therefore this is the direction, because it's not a composite composite has young modulus in the one direction, young modulus in two direction. So for our case, we don't have any, so because steel is just an isotropic material, alright, and therefore no need to explain. Alright, E1 and E2 are the same. So likewise for their Poisson ratio. Alright, so in other words, if it happen that if you don't know what is isotropic is same strength in all directions. When you push this, you push in any of directions, the strength is all the same. Alright, if it's anisotropic, then it's maybe strong in this, for composite, right, it's strong in this direction but weak in this direction. Okay, so therefore hopefully you are clear. So therefore in isotropic materials, we don't see this sort of thing happening. So therefore the Poisson ratio is 0.3 for metal. For steel, and it's not given, so you need to actually also memorize this type of little stuff, or table is provided. So we know that the Young modulus is 210 GPa, or given over here, right? The Young modulus of steel is this dude over here. Okay, so once you set this up, alright, plus, alright, 1 minus 0.3 square also, and therefore if you were to solve for this, 0.00866, 1 over GPa. Alright, so therefore you need to change, right, because it's 1 over E, and you want to find the equivalent Young modulus, so you bring this down, you bring the E out. Alright, and therefore E is equals to 1 over 0.00866. You'll get 115.4 GPa. Alright, and please take note that there will be a trend. Alright, please rewrite this as in the form of 115.4 times 10 to the power of cube megapascal, because gigapascal is 3 times larger than MPa, so therefore times 3. Because I think the stress max, they want us to write in terms of MPa, so it's easier. Or I leave you to think about it lah. Actually no need lah, you just leave it as GPa first. So once we get this E, alright, this equivalent Young modulus actually is we're almost there already. So let's find our stress max then. Alright, you wonder why do we want to find stress maximum? Alright, because we want to use this stress maximum, alright, to find our Brinell hardness of the softened material. Alright, the Brinell hardness of the softened material, if you, alright, the H, where is the H actually? Give me a while. Okay, never mind. So in order to find the Brinell hardness, right, the BHN, maybe I should write it down. You need to use this one, the Brinell hardness value. Okay, it's not given to you, so you need to know. So in order to solve for this value, you need to have a stress maximum. Alright, and therefore this is why we are solving for the stress maximum. And therefore I'll just plug it in and place it over here, since we're almost there already. So this is the fourth step. So you just simply apply only. W is the load, alright, the compressive load, as we say, the compressive force 100 Newton. Alright, and then over here this is in terms of what? E, right? E is the Young modulus. Sorry, just not have a phone call. But anyway, so this E is actually this one, 115.4 GPa, which we have found the equivalent Young modulus. So just sub it in only. And then over here this is the R, the contact radius, we have found also. So just sub it in only. Alright, but please take note of this thing. Alright, be very careful. This is 60 millimeter. Alright, this is, everything is in terms of Newton. Alright, this is in terms of megapascal, or in other words, mega Newton per meter square. So therefore be careful of this value. Alright, this should be 0.006. I think you give me a while. Yeah, it should be 0.06 square. Okay, let's work it out and see whether that, okay, the answer is actually given from the lecture is 474 MPa. Alright, so let's see whether is it 474. You give me a while. Forgot there is actually a square over here. The Young modulus is a square. Alright, and please take note that when you calculate in your calculator, right, before I get the answer, is that this thing over here is within the 1/3. Alright, this thing over here is within the 1/3. When you put calculation, don't calculate for this thing first and then you 1/3. Alright, don't, it's a very careless mistake. Alright, so therefore be careful. Do this first and then 1/3 cube root and then multiply with 2/3. So therefore let's calculate for the answer now. If I were to use 0.06, I will get 47.7 GPa. Okay, if I were to use his method, alright, although I think it may be wrong, alright, because he's using 60 millimeter. He's using, instead of 0.06, he's using 60 millimeter. When everything is in terms of Newton is in terms of meter, everything is in terms of meter. Alright, so this is something that you should be careful of. But if you were to use his method where he sub in instead of 0.06, he sub in at 60, let's see what's the answer. It's 447 MPa, which is exactly the same as his answer. Alright, his answer provided is 474. Okay, so I think he calculated that through his own manual calculation. But I would think that this has certain flaws in there. Alright, but don't want to confuse you anything, let's use the 474 MPa instead. Because his answer is in terms of all this thing. Alright, but take note that all in all you need to memorize this following equation. Alright, in case that you forgot this thing, the contact radius equation, equivalent Young modulus equation, alright, and nonetheless the last part of this thing, the Brinell hardness equation. Alright, so we know that this thing over here is 474 MPa. So what you're gonna do is just to calculate. You get 144.9, alright, kgf per meter square. Okay, so I think you see meter again. So I think maybe most probably his careless mistake. But anyway, be careful. So we should, in terms of GPa now, it should be 47. But anyway, yeah, let's stick to his answer. Okay, so it should be, if you round off, is 150 kgf per meter square. And please take note that it's in terms of meter, so there's a certain discrepancy in the value, so I need to check, double confirm. Alright, so this is how you find your minimum level of Brinell hardness. Alright, hopefully you know already. So next, we haven't finished yet. Alright, we have to find our depth to avoid the plastic deformations. So you need to find your A. Alright, your A value. So before that, let's return back to this part. Alright, during calculation, right, please calculate this thing first and square it. Alright, don't type in like 100 times 105 times, you think that 3 and 2 are the exponential, so you multiply together, become 6. Alright, wrong. Alright, be careful of the careless mistake. Alright, it's like that. Alright, 115 times 10 to the cube square. Okay, so hopefully, yeah. So let's come back to these equations over here. A, your depth. So we need to find your impression radius. You know your R, you know your E. I'll not evaluate for you already because it's pretty straightforward. So what I have over here is 0.34 mm, or it is equals to 340 micrometer. Alright, so I think so far he's still using the contact radius as 60 millimeter instead of meter, and over here is in terms of meter, Oh, anyway, so okay, so never mind. This is in terms of millimeter. This A is in terms of millimeter, so okay, should be fine. Sorry. But over here, definitely something is wrong. Alright, so this thing over here is 0.34 mm already, and it's 340 micrometer. Okay, so if you remember the 0.6 thing A comes already, to avoid plastic deformations. Alright, so how do you cause if I'm not wrong, your ball bearing is over here, your steel ball. Alright, so this thing over here is your copper material. In order to cause your copper material to deform, alright, it doesn't mean that you're gonna exceed the yield stress. Alright, it doesn't mean that you exceed the yield stress, it deform. You need to exceed the yield stress also, as well as exceeding the shear stresses. Alright, so the shear stresses is somewhere around this region. Alright, 0.6a. So in order to avoid these plastic deformations, your steel ball has to be around 0.5a. Alright, the minimum. Alright, its minimum is 0.5a. So if you were to multiply with this thing, you'll get about 170 micrometer. Alright, so this is the answer for the minimum depths to avoid plastic deformations. So one thing you may wonder, alright, is that what is the depth? Alright, A is the depth already. We just not say is the imaginary axis A. Alright, so if it's 0.5a, alright, then it should be somewhere in between here. Alright, actually you can leave the video lah. I just want to talk to myself and for the future also, for my own future. So yeah, I'm keen to understand what is the question behind that, because A is already the depths, and then what type of depth are you talking? Alright, so a bit weird, right? So I also don't know what the hell is going on. So I just want to raise this awareness. So if it's 0.5 for example, then this is the amount of depth. And therefore, what do you mean? One thing is that you can pause the video and take screenshot and read page 19, alright, in the future that you need it, because currently I still can't figure it out why. Alright, this is already imaginary. So if I have, for example, this is the ball bearing. So if I have at the depth of this part, alright, 0.5a, what is this meaning? Yeah, seriously, I don't know, man. Come on. Yeah, I don't know the meaning of that lah. Then over here it says shear stress occur below surface at 0.5, below the surface. So below the surface, so over here this is the thing. So over here this should be the radius, for example. Alright, so below the surface 0.5, so the shear stress may be over here. So the depth, so and its depth to avoid plastic deformation. I was thinking, perhaps I may be wrong, is talking about certain dynamics, alright, where this is the steel ball, for example, okay, and you kind of like, once you impress onto it already, and then you start to move again, alright, you rotate, blah. So the next time when you hit 0.5a at this point over here, when you hit it, alright, you'll start to cause deformation. You get what I mean? So at first, the first impression, right, the first impression radius when you impress is this area. I mean this A, this so-called imaginary radius, the blue color one. Okay, which is this one. Okay, which this one. This is the imaginary radius, the impression radius. Alright. So if the second time, if you were to go, because this is a ball bearing type of thing, right? Where am I? Give me a while. Your ball is over here, then you rotate. So over at the surface, alright, over at the surface over here, is rotating. So the next time when you hit this part and then hit it, or if it's at 0.5a, it will start to deform. So in other words, the blue color one over here will start to deform. It will start to create this type of so-called wear, I should say, or this type of portion where some part of the thing will break off, and then over here you'll cause certain breakage also, things like that. So I think this will make more logical sense, but yeah, I may be wrong. And I think this is it. These are the answers lah. Alright, 117 micrometer for the depth, alright, which is 0.5a, and this thing. So the things that you need to highlight are 3 equations. Alright, you need to memorize your mean contact radius, alright, and your equivalent Young modulus equation, as well as the Brinell hardness equation. And you also need to know that your R1 radius and R2 are, R1 is the ball bearing, ball radius of the ball, R2 is the plate, alright, the inner plate, and the rest should come naturally already. Yeah, so I'll see you in the next video for part 1C. It's a very short video, so see you there.